Hi guys, in this video, I'll be discussing significant figures, which are very important topics that we will be seeing throughout this semester. So it is important that you learn about significant figure and understand it now. So first, I will discuss the rule of significant figures and then how to convert between a decimal number and a scientific notation that will allow us to retain the same amount of significant figures. So first, let's define what significant is and why is it important that we have to learn about it. Now here's what happened right here. In chemistry, we deal with measurement a lot. And anytime that we make a measurement here in science, then we know already that a measured quantity cannot be completely accurate without uncertainty or error in them, right? And it doesn't matter what kind of equipment that we have, regardless of the equipment, whether how expensive or how fancy they are, all equipments will have some error associated with them. And we call that the systematic error. So error that are due to the instrument, because the instrument themselves have error in them. So therefore, if we use that instrument right there to obtain a measurement value, then we would have some degree of errors in our value as well. And the other types of errors is called the random error. And this kind of error right here are due to the limitations of the person performing the experiment, right? The thing that we can't control. And so we call that the random errors. And because again of these two types of error right here, this is why that there will always be uncertainty in our measurement. So once we obtain a measured value and they have uncertainty in them, it is then very important that we report our value in such a way to let other people know whether the uncertainty exists in our measurement. So that way, all the people, when they look at us, our value, they know exactly how much to trust our value because they know whether the uncertainty exists in our measurement. And so to report the uncertainty in our value, we need to follow the guidelines of significant figures, which I will discuss to you in a little bit. And when a value is reported correctly using significant figure, we'll be able to figure out which digits are accurate and which digits are not in a measurement. And we'll also be able to determine how many significant figure a value have and know where the uncertainty exists. So here are the rules for significant figures right here. When we take a look at a number, we need to be able to determine how many significant figure that it has and where did the uncertainty exist in those values using this rule right here. So first, all non-zero integer are significant. So these are values from 1 to 9 and they are always significant. And leading, rule number 2, leading 0 are not significant. And in fact, they are never significant because we add them in simply for cosmetic purposes because they are used to locate the decimal point. And rule number 3, embedded 0 are significant. And embedded 0 are basically 0 between non-zero integer. And lastly, trailing 0 are significant. And they're only significant if the decimal point is been specified in the value, but not implied. Okay, so if the decimal point is being specified in the value, then that when the trailing 0 would be significant. If we were to have an implied decimal point, that when the trailing 0 would not be significant. So let's try an example right here so we can learn how to then identify all of this value. So first one, this 30 right here. This 30 right here are referred to as the leading 0. So leading 0 are 0 that exist before non-zero integer. So despite whether the decimal point exists, if the 0 exists before a non-zero integer, all of those 0 will be classified as the leading 0. So in this case right here, they are not significant. So SF stands for significance. And now moving on to this number 3. So this number 3, this number 7, and this number 8 right here. These 3 values right here, of course, are significant because they are non-zero integer, right? So all of this are significant. And now the 2 0 in here between the 3 and the 7, this are then called the embedded 0. And embedded 0 are significant. And lastly, the 3 0 in the back. This 3 0, these are called the trailing 0. So trailing 0 are the 0 to the end of the number. And in this case right here, they are significant. Why? Because the decimal point is actually specified in this value. So there it is, we see a decimal point. Or this number right here has a specified decimal point. So therefore, this trailing 0 would be significant. And now, when we count how many significant figures are there together, we'll be counting all of the value that's significant. So we can see that this 3 is significant. So 1, this 2 0 are significant, this 7, this 8, and all of this 0 are significant. So overall, this value have 8 significant figures. So that's the rules how to determine how many significant figures that exist in a value. And now, here are some important points that we have to make sure we remember. When a value is written correctly in terms of significant figure, it then follows that the last digit that is significant, that's where the uncertainty exists. So here in this case right here, looking at this value right here, the last digit that is significant will be this 0. So in this value right here, this is where the uncertainty exists, meaning all of the digits before this are accurate, and this is the inaccurate value right there. And we'll go over some of those examples in a little bit. And now, the second important point, the position of a value is not determined by how big or how small the value is, but it determined by where the uncertainty exists. So it actually depends on which digits that the uncertainty exists that tell us how precise the value would be, not how big or how small it is. And again, we'll go over one of that example in a little bit. And the third important point, when converting between a decimal notation to a scientific notation, make sure the amount of significant figure remain the same by carrying the significant 0 over. Because as we convert between the decimal number and the scientific notation, the value of the amount of significant figure is not supposed to change, right? Because if they were to change, then now we are gaining or losing the certainty in our measurement. And that is not supposed to happen when we convert a value between decimal number to a scientific notation. And for a scientific notation, we can determine how many significant figures that it has by looking at the coefficient or the decimal part, but we are not looking at the exponential part. So these are the 4 important points that make sure we remember as well. And now let's go over an example right here. So here in this case right here, 3100. So in this case right here, how many significant figures does this value have? That we can see in this case now, very important. All value will have a decimal point in it. But here in this case right here, there is no specified decimal point, right? But however, we would be implying this value right here has an implied decimal point. And the implied decimal point, so DP stands for decimal point, will locate right there. But it is not specified, it is implied. Okay, so in this case right here, we can then see, following the rule of Sig Figs that we have seen above already, this 2 value will be significant. And in this case, this 2 0 right here are not significant because the decimal point is not specified. So therefore, this value will have 2 significant figures on it. And now, the last significant figure that is uncertain, that is significant, that is this one right here. So this is the last digit in this value where the uncertainty exists. Okay, so in this case right here, what this telling us is the following. This value right here have uncertainty exist on the 100th place, because this one right here is the 100. On the 100th place. So therefore, the uncertainty in this value right here exists on the 100. And when we convert this into a scientific notation, this would then equal the following: 3.1 times 10 to the third. But we are not carrying this 20 right here over because this 0 right here are not significant. Okay, so 3.1 times 10 to the third. So, and now let's try another example over here. If we were to have 3100 with 0.00, then here in this case right here, we can then see that, let's now count Sig Figs in this. In this case right here, the 3 and the 1 are always significant. And now in this case right here, this 40 are also significant as well. And the reason why that is because the decimal point is being specified. So this is being specified. And that's why the trailing 0 would be significant. And now in this case, all of these are significant. So we have 1, 2, 3, 4, 5, 6 significant figures in this value. And now the last digit that is significant would then be the last 0. So this last 0 right here. And that's where the uncertainty exists in this value. So the uncertainty exists in this case right here on the second decimal place, or on the 100th. So on the 100th place, or on the second decimal place, that's where the uncertainty exists. So therefore, we can see that this value right here is actually quite precise. Between these two values, this value right here is more precise compared to the first value. And the reason why that uncertainty exists on the 100th of the second decimal place, versus here on this value, the uncertainty exists on the 100. And now the more place where the uncertainty exists, then the less precise it would be. For an example, uncertainty exists on the 1000 would then be less precise compared to another value where the uncertainty exists on the 100. And when we convert this value right here into a scientific notation, it would then equal to 3.100, and we have to carry all of this 0 over, okay, because all of those 0 are significant, followed by times 10 to the third. So when we take a look at the scientific notation and count its Sig Fig, we will be using its coefficient, or the decimal part. In this case right here, 1, 2, 3, 4, 5, 6 significant figures. And now let's try some of the practice problem right here. So given this following decimal number, determine how many significant figures that they have, and then convert them into the appropriate scientific notations. So let's give this one a try. So here in this case, this is the example that we have seen already. So this value have 1, 2, 3, 4, 5, 6, 7, 8 significant figures. These 3 trailing 0 right here are significant. So 8 significant figures. And when we convert this into the scientific notation, so we have to move the decimal to the right 3 times, right? So 3.0078, and now we have to carry the last 30 over, followed by times 10 to the negative 3. And now moving on to the next example, this value right here. So when how many significant figure did this value have? So here in this case right here, this 0 is not significant, right? Because that is the leading 0. So we have 1, 2, 3, 4, 5. So this value have 5 significant figures. Okay, and now when we convert this into a scientific notation, this would then equal to 7.8934 times 10 to the negative 2. And now on this value right here, the uncertainty exists on this digit, versus the uncertainty would exist on this digit right here. So when we compare between these two values right here, this top value right here would then be more precise compared to this value. And then again, it actually where the uncertainty exists that help us see which value is more or less precise. Okay. And I'm moving on to this next example, 40,000. So in this way right here, how many significant figures do they have? And the answer would be 1. Now, in some textbook, this value right here is referred to as an ambiguous value. And what that means is that the value is not clear. And it's not clear because there's a lot of uncertainty in it. Okay, and so some textbook might call this an ambiguous, but then they don't determine how many significant figure that it has. However, if we were to count significant figure, it would be 1. Okay, so don't just say ambiguous, but make sure you state how many significant figure that has. And I make this value right here 1 significant figures. So the uncertainty exists here on this 4, and that is the 10,000 place. So there's a lot of uncertainty in this value, in which that this value is as follows. It can be 1 value higher or 1 value lower. So normally that's the meaning to value. The uncertain value can be 1 digit higher or the 1 digit lower. So in this case, we can have anywhere between 30,000 to 50,000. So that's the meaning of this value right here. And because it can vary so much, this is why that it is referred to as an ambiguous value and have 1 significant figure in it. And when we convert this into a scientific notation, we then equal to 4 times 10 to the 4. And again, we are not carrying this 0 right here over, because this 0 are not significant. And now, the next example, 40,000 with a decimal point. So here in this case right here, because this decimal point is being specified, therefore it makes all of this 0 right here significant. So we have 1, 2, 3, 4, 5. So 5 significant figures. And here in this case right here, the digit where the uncertainty exists would then be this value right here, this digit. Meaning, so basically this is where the uncertain digit. So all of the digit before this would then be certain. Okay, so please remember that. It then follows that the last values that is significant, that where the uncertainty exists. And that value can be 1 higher or 1 lower. And when we convert this into a scientific notation, we have to make sure we carry the 0 over. So we have 4.000 times 10 to the 4. So that's the differences between these two values. This 40,000 is much more precise compared to the previous 40,000 above. And now 40,000.00. So here in this case right here, all of these 0 are significant. So this value right here we have 1, 2, 3, 4, 5, 6, 7. 7 significant figures. And now the uncertainty would exist in this last digit right here, 0. So basically in this case right here, the uncertainty exists on the 100th or the second decimal place. So this value right here would be more precise than this value above, and this value is more precise than the value before it. And when we convert this into the scientific notation, this would then equal to 4.0000 with the 2 extra 0 times 10 to the 4. And now let's try another example right here. Problem number 12. For the value below, rank them in order of decreasing precision. So we need you to determine which is most precise and followed by which one. So these are the different value right here. And again, please remember this. It's actually where did the uncertain digit exist that make the value more or less precise than the other, not how big or how small it would be. So in this case right here, when we look at all of this value, you can see that these two value right here are really big value, right? But then again, how big or how small it is has very little to do with its precision. Okay, so now we need to underline how many sig figs that each of this value have and take notice of the digits that is uncertain. So here in this case, this value have 3 significant figures, and on this 3, that's where the uncertainty would exist. And now we can see this is actually existing on the 10,000 place. Okay, versus this value have 4 significant figures, and the uncertainty exists on this second decimal place. And this value right here have 2 significant figures, and the uncertainty exists on the 4th decimal place. And this value it has 1, 2, 3, 4, 5, 6, 7, 8 significant figures, and the uncertainty exists all the way in the back. So we can see this value right here is very, very precise. And now this value right here have 1, 2, 3, 4, 5, 6 significant figures, and the uncertainty exists on the one place. And now this value right here have 1 significant figures, and yet uncertainty exists on the 10. And now, so by looking at all this, we can see that this value right here is most precise. And again, it's actually dependent on where the uncertainty exists that make it more or less precise. The more decimal places that it has that is significant, then the more precise it will be. So first, it will be this value, followed by this value, and then followed by this value, and then followed by this value, and next will be this one, and lastly this one. So that's how all of this value right here are ranked in decreasing order of precision to them. And again, please take notice that sometimes, so it's actually just not how many sig figs that it has that determine how precise it is. Okay, but it depends on where the uncertain digit exists. Please try the rest of this 2 problem.